So today we are going to look at the motor effect. Firstly, what is the motor effect? So to consider this, we need to use two magnets, one north with one south, facing each other. We should be aware of the fact that magnetic field lines or flux lines move from north to south. So if you put a current carrying wire, or a wire that is carrying a current, into a magnetic field, like so, you have two magnetic fields combining, which puts a force on the wire. The force can make the wire move out of the magnetic field lines of the magnets. So note, to experience the full force, the wire should be at 90 degrees or right angles to the magnetic field lines. So the next question that we need to ask ourselves is, how does the magnetic field lines combining cause the wire to move? And to consider this, we must look down from above this scenario. So you can see I've drawn an eye there. Again, eyes are a bird's eye view. If we look directly down on it, you will still see our magnetic fields, which have our magnetic field lines, like so, moving from north to south. Note the colours that I'm using here, as they will show the changes that will occur. If we look straight down, you will see our wire. So as you can see here, the black dot is looking straight down on top of the wire. As the wire is carrying a current, it too will have magnetic field lines around it. These are going in concentric circles. And a key thing that we need to note here is the direction of these arrows. So if we look at arrow 1, it is pointing in the opposite direction to arrow 2. Because these arrows are going in opposite directions, they will repel each other. Whereas in the latter stage, the arrows there are going in the same direction. So they combine the magnetic fields of both. As the top half is repelling each other, the magnetic field lines at the top have to go behind the wire or underneath the wire. This causes a change in the direction for these magnetic field lines. So they are getting deflected. Alright, so the black lines are the deviated magnetic field lines. And notice the density of these. Because of all the magnetic field lines are very close together here on one particular side, it creates a force, a resultant force which causes the wire to be pushed out. So it pushes the wire out of the magnetic field. So how could we increase the force? So to increase the force, you should increase the current on the magnetic field strength. So again, we have our scenario here. And the next question that we are going to ask ourselves is, how do we know which direction will the wire move? So will it move to the right or to the left? For this, you need to use Fleming's left-hand rule. So what is Fleming's left-hand rule? So for Fleming's left-hand rule, F stands for force, or the direction of motion, which should be indicated with your thumb. B is the direction of the magnetic field lines or flux lines, and that would be your first index finger. And I, which is the direction of current, which will be your second index finger. So if we look at the following diagram, which direction will the wire move? So B, the magnetic field lines are running from north to south. Okay, so this is your direction of B. The current is moving up the wire, so the eye is pointing upwards. And if we rearrange our hands, so give yourself a minute and try and do this, the force will cause the wire to move out the way. So our wire will move, or will experience a force to the right. Okay, so we'll move in to the right. So here's an example that I want you to have a go at. Which direction is the force on the wire? So have a little look at this example, pause the video for a minute and have a go. Okay, so first thing that you should do is draw an arrow for the current. So remember the current goes from positive to negative, so the arrow will be pointing up. Next thing, draw an arrow for the magnetic field direction. So magnetic field lines should always go from north to south. Thirdly, line up your fingers with arrows from the above using Fleming's left-hand rule. Remember, it's using your left hand, so be aware which hand you're using. And finally, draw in the direction of the force, according to which way your thumb is pointing. So whichever way your thumb is pointing, that's the direction of the force. And for this example, it should be in this direction. Keep practicing these until you figure it out. So, how do we use this motor effect to create a simple electric motor? So again, we set up our example. However, this time we're going to use a coil of wire. We'll have our north and south pole, which we should already now know that the magnetic field lines move from north to south. And we will have one end of our wire, or one end of our coil positive and the other one negative. So our current will move from positive to negative. For this, we will use Fleming's left-hand rule, so we'll know the direction of the magnetic field lines, we know the direction of the current. So on one side of the coil, you'll notice that according to Fleming's left-hand rule, if you do it on this, it will show that the force is pointing up the way. However, if we look on the other side of the coil, the current is in the opposite direction. Because the current is in the opposite direction, the force becomes pointing down the way. This causes the coil to rotate. Because one points up and the other force acts down, it causes the whole coil to rotate. So, the coil of wire will rotate, but only half a turn. This is because if we look at the positive and the negative, when the positive and the negative sides switch sides, the current is reversed, and so will the rotation. So if we cause the coil to turn, it will swap the sides of the positive and the negative. And when the positive and the negative swap sides, the current goes in the opposite direction. And because of this, the rotation will go back the way. So what it means is that it will not rotate a full circle, it will flip back and forth, only doing half rotations. So the next question we need to ask ourselves is, how can you get a complete rotation? And for this, we use a little device at the end. And this is called a split ring commutator. And what it does is it constantly keeps one side of our coil negative and one side positive at all times. So it stops that positive and negative from rotating. And however, the coil itself can continue to rotate inside this split ring commutator. So, the split ring commutator swaps the contacts every half turn to keep the motor rotating in the same direction. So, it essentially keeps one side positive and negative while allowing the coil to complete whole rotations. Note: an electric motor requires a direct current, a DC current. Direct currents only flow in one direction. If you use an alternating current, it wouldn't work. It would constantly flip back and forth. All right. There are 4 factors which speed up the motor. So 1, increase the current. Secondly, add more turns on the coil. Thirdly, increase the strength of the magnetic field. And finally, add a soft iron core inside the coil. So what do we use this for? So again, we'll have our diagram here, but what I'm going to add this time is an axle, a metal bar on the inside. And when the coil rotates, so will the axle. And if we were to put a fan or a propeller at the end of this will also cause it to rotate. So essentially this is how a fan or a propeller works. This can be also used for food mixers, whisks and CD players. So another example for you to try out, just to practice your left-hand rule, is in this example, is the coil going to turn clockwise or anti-clockwise? Again, give yourself a minute, practice doing this question and pause this video. Turn on once you have it complete. Okay, so first thing that you should do is again draw the current. So this will be going from positive to negative. Next thing you should do is pick only one side of the arm of the coil. So for this example, we are going to pick the right side. Use Fleming's left-hand rule on this side of the arm or the coil, and then draw the direction of the force or the motion. So for this example, when we carried out Fleming's left-hand rule, the force pointed up the way. Because the force is pointing up the way, this means that the coil is going to rotate or turn in an anti-clockwise motion. Hopefully this lesson is of some help to you on electric motors and the motor effect.